Thank you for joining us for today's webinar. It is part of an ongoing series developed as part of an FDA-funded project called A Targeted Learning Framework for Causal Effect Estimation Using Real-World Data. Today's webinar is titled Introduction to Bayesian Additive Regression Trees, or BART, for Causal Inference. Our speaker is Dr. Nicole Bohme Carnegie, Assistant Professor of Statistics in the Department of Mathematical Sciences at Montana State University. Dr. Carnegie specializes in causal inference and infectious diseases. She has successfully used BART in several predictive modeling and causal inference competitions and developed tools for sensitivity analysis when using BART for causal inference. Dr. Carnegie obtained her PhD in statistics from the University of Washington and completed postdoctoral training in the Department of Biostatistics at the Harvard School of Public Health. Dr. Carnegie, thank you for being here with us today.
Thank you, Susan, for the introduction and also for the invitation to give some introduction to using BART for causal inference for this webinar series. I'm excited to be here today. So I just wanted to start out by giving sort of a roadmap to what I'm going to be talking about today. So first off, building from the ground up, what are additive regression trees in the first place, and then why Bayesian in this case, and then digging more into the use of BART for causal inference problems in particular. So the building block of BART is regression trees, and the basic idea for a regression tree is that it's an algorithmic partitioning of the observed data into non-overlapping subsets with the goal to minimize the variance in our response within the subset. So we're trying to find sort of clusters, in a sense, of observations that have similar values of the response that are somehow defined by values of predictors that we are including into the model. And so then the resulting regression fit is just the mean of each subset. So it's a non-parametric approach that is not assuming any particular functional forms, strictly partitioning the data and then taking the mean within groups as our prediction or our fit. So to give an example of what this might look like, this is a figure from a paper that I wrote, but I kind of like it. So if we have a situation where we just have one predictor, this X value, and our response Y, what a regression tree might do is say first split somewhere around X equals 80 because the values above that range are more similar to each other than the values below. And so if we're thinking about creating an estimate for a particular observation, this is our first decision point in the tree, is our predictor value less than 80. And then maybe in this case, we have one more split somewhere about 90, where we're grouping then this sort of exponential piece of the curve into two subgroups. And so then for any observation, our regression fit, or our estimate of the response given this tree model is just, we drop down this decision tree and we say, all right, if I'm looking at this point right here, is X less than 80? Yes, it is. So my best guess is just the average of the Y value for all of these observations, which is 26.2 in this case. If we're looking at, say, this observation up here, is X less than 80? No. Is it less than 90? No. So then we're dropping down into this terminal node and say, estimating a mean of about 42.8. And so the fit from the tree then can be visualized as these horizontal red line segments. So this is our essentially step function that is the regression that we get from this algorithm to partition the data. So that's a single regression tree. What we're using when we're talking about BART are additive regression trees. And this is because if we do stick with just a single tree, that's going to place a lot more emphasis on interactions. So in the plot that we just saw, that's not possible. There's only one predictor. But it's also going to have difficulty finding linear relationships. So just to take a couple of examples, if we do have a situation where everything is truly linear, like we have on the left here, fitting a linear regression, right, we get two parameters, an intercept and a slope, and we have an estimate that follows this whole pattern for the full range of our x values. If we're thinking about this partitioning approach, and the resulting step function, the first partition is probably going to be in the middle because the bottom half are more similar than the top half, but then the estimates are going to be pretty far away for the ones close to the partition or to the boundary. And so maybe we partition again, and it's going to have a hard time coming up with that step function that follows this linear pattern without making a lot of splits. On the other hand, over here, if we do have, say, two groups, the red and the black, probably the first split or a very early split is going to be on whatever covariate is defining these two groups, because we definitely have very low variability within x2 equals red, and more variability with x2 equals black, and then there might be further splits to try and capture this sort of linear approach. But if we're trying to limit the depth of our trees, we're going to put a lot of emphasis on the difference between these two groups, and then maybe break down group 2 up here into a couple of nodes and sort of underspecify the clear relationship between the response and the predictor within that particular group. Why are we not going forward? There we go. So the alternative is, rather than fit one tree, which might have to be very deep to capture patterns in the data, we can fit many small trees using a backfitting algorithm. So the basic idea is we take one small tree, maybe 1 to 5 splits, say, tops, and then get the fitted values from that tree for each observation, subtract those from the observed, and then fit another small tree to the residuals. So we're trying to capture whatever variability wasn't handled in the previous small tree, but not with this extremely nested structure where the splits are all, in some sense, you can think of nested splits in these trees as when we're dealing, for instance here, if this was x1 and this was x2, in some sense that's implying some sort of an interaction. So if we start getting down to very deep trees, we are in some sense suggesting that there are 5 8-way interactions, and that's a little bit much. And so here we keep it shallow, but we still try to capture any variability that hasn't been absorbed using a previous smaller tree. And then this process is repeated until we have some number of small trees. It's usually a fairly large number, and sometimes left as like a tuning parameter for these regression approaches. The caveat here, because this is non-parametric and we're essentially just partitioning the data into smaller and smaller groups to try and achieve reduced variability in our response, is that there's a very real possibility of overfitting. So if we don't specify some mechanism to control the fit of the tree, any tree-based model can easily overfit the data. So for instance, coming back to this example, if we just let this single tree grow arbitrarily, as long as the variance, the within terminal node variance continues to go down, ultimately what we probably end up with is a single observation in each terminal node. And if you have exactly that value of X, then you end up with an estimate that is exactly the value of Y for that observation. But that is extremely unlikely to be a reliable predictive model in any other setting, right? This is clear overfitting to the data. And so ways that we can try and get around this are limiting the tree depth, right? So if we say we're going no more than 10 steps down, then you can't end up with each observation in its own cell. And then another approach is using shrinkage. So boosted regression trees, which is the sort of perhaps non-Bayesian analog in a sense to BART, you can limit the tree depth, and it's usually specified. So tree depth is 3 splits, for instance, and that is as far as it will go. And then also uses shrinkage to multiply the fit of each tree by some small constant to essentially leave behind a little bit of the variability that this particular small tree is supposed to be explaining in the data. And in this setting, that either or both of these, but typically certainly the shrinkage as multiplier, would be chosen by cross-validation to find the value for that shrinkage parameter that optimizes the predictive performance of the boosted regression tree model. If we're talking about a single tree model, we might use cross-validation again, but here it would be so pruning branches in that decision tree that aren't robust to the removal of some observations. So the final decision that splits 2 observations each into their own bin is unlikely to be something that is supportive if we happen to do a cross-validated sample and one of those observations is no longer in our sample, right? So this gives a way of trying to establish at what point we cut off the splitting because it no longer is improving the predictive performance of the tree when applied out of sample. BART takes an approach essentially similar to the boosted regression trees, the difference being that the depth of the trees or the shrinkage shrinkage factor are set via priors. So rather than taking that computational step of cross-validating those to try and find something that's optimal, the priors have been investigated pretty thoroughly. They seem to be the default settings in most R packages, for instance, that will fit a BART model, seem to work well across many settings. But they're also, as priors, something that is not completely hard and fast. Like in the boosted regression tree case, if you set a tree depth limit of 3 splits, that's as far as any of them can go, even if the data would suggest that something more complex might be appropriate. All right, so that's caveat when using regression trees in general. The advantage, because it is so very non-parametric, is that you can capture very complex response surfaces is the way I think that applies across the board. Very complex response surfaces without having to continually revise, what needs an interaction, what needs a higher order term, what improves and what doesn't improve. So this is just an example. It's taken from a paper by Jennifer Hill, which was sort of the first one to introduce BART as a causal inference tool, where we have two groups in this data set, one for whom the response curve follows, the black lines here are the true curves, the relationship between this predictor X and the outcome. And then there's two groups, each of which have a different curve that they're following. In this case, it's treated versus control was the idea. And what you can see is if we fit a single tree, we get something that kind of approximates that black curve in a very rough sort of stepwise way, but we're at least getting the fact that these are following distinctly different patterns depending on whether they're in the treated group or the control group. And then the BART fit is this red dashed line here, and you can see that it follows the actual quite closely, actually in some ways surprisingly closely, given that there are not all that many data points in here, although the variability is pretty tight around those curves. Aside from places where there's not a whole lot of observations to be had, which is, no statistical model is going to have a whole lot of certainty when there's no data to inform it, right? And this extends then to much higher dimensional settings where it's much more difficult to visualize the shape of the response surface and what the differences might be between particular groups. So by adding all of these small trees, we can end up with pretty smoothly varying estimates of complex response surfaces. And we'll see a little bit later that this is really where the advantages for causal inference in particular come in, is having this ability to accurately map relationships between the observed variables and the response. All right. So the BART model then is a sum of trees model with a regularization prior. Let's say that 3 times fast. And so we're modeling our response as a sum of these G of Z is going to be a treatment variable if we're talking about causal inference, X are covariates, and then our tree model with some normally distributed noise at the end. So the only sort of parametric piece here is that we are assuming that whatever is left over after we account for the response surface through the sum of trees is then just Gaussian noise around that surface. And so our tree model is defined by the trees themselves. Oops. And then the associated vector of means in the terminal nodes of that tree. And then this G notation is just for the value that we obtain by essentially dropping some observation down the tree and finding what the mean is for the terminal node that it lands in. The prior then, which is what makes the Bayesian form of this kind of nice, is there's a prior preference for the trees to be small, so not very many terminal nodes. Most of the weight is put on trees with 1 to 3, some weight on 4 and 5, and I mean non-zero for larger trees, but by and large they're constrained to be quite small. There's a shrinkage prior that shrinks the means towards 0. So that's that the shrinkage that we saw with the boosting as well. And then there's a prior on that residual variance that suggests that it's somewhat smaller than if I just did a ordinary least squares regression of y on all of my predictors or covariates. Whatever variance is left over from there, we're going to assume that we do have somewhat less once we can map the complex shape of the response surface, but perhaps, at least according to prior knowledge, just somewhat less, and we see if it gets a whole lot smaller. So why Bayesian? And there's a few reasons that I think are pretty strong here. First of all, the data can overcome assumptions about the depth of trees or the level of shrinkage needed, because the prior encourages very small trees, a certain level of shrinkage towards zero, but it is not a fixed value. Whereas, for instance, in boosted regression trees, you might say that I'm going to have trees no deeper than 3 splits, and that can't be, even if the data suggests that that's needed to go deeper, it can't happen. We do still have a tuning parameter of the number of trees. In my experience, it doesn't make a huge amount of difference, so you probably don't need to do cross-validation on there to find an optimal number of trees, but you could. So we can overcome some assumptions. There's computational benefits from avoiding cross-validation on depth of trees, shrinkage needed, so we're having a more data-informed approach to that. Like I said, you might still want to cross-validate the number of trees, but I would say it's typically not necessary. But the biggest thing from a statistical perspective is that this embeds what is normally an algorithmic approach in a likelihood framework. So as with many machine learning approaches, the idea of a tree is it's extremely flexible. It can do a good job with prediction, but it is difficult to assess exactly how uncertain the resulting estimates are, and obtaining coherent uncertainty intervals from most machine learning approaches is extremely difficult, if not impossible. They're not developed in that framework. It was not the goal. And so one of the things that's extremely nice about BART is that we can associate a level of uncertainty with estimates of things like causal effects, while still reaping the benefits of having a flexible machine learning based approach to finding what those are. All right. So why? So that was sort of BART in general. What is it? Why Bayesian? So now why use it as a causal inference tool? And I would say there are a couple of benefits. One is that the very precise modeling of the response surface corresponds to much more thorough control for confounding than we would get with a traditional parametric model. So in a causal inference setting, if you're doing a parametric, a logistic regression, right? We'll say that we are estimating the impact of our treatment, controlling for, age, education, whatever. But we're controlling for them in a particular form. So we're assuming either that linear response with the transformed mean, the mean on the length scale, or maybe we've put in a quadratic for age because we think that there's a pattern there. It's still a very parametric relationship. And so if we have a situation where that is not the shape that the response surface actually takes, we're still only getting partial control of confounding due to whatever we have in our model. And so it doesn't get around the issue of unmeasured confounders any more than any other causal inference tool does, but what it does do is do a very good job with the ones that we have measured in terms of complete control of the confounding relationship. The other advantage is, while it takes a little doing to explain what the model is, actually estimating causal effects from the resulting posterior distributions is straightforward. And this is both average treatment effects, and if we think there's heterogeneity in our causal effects, either by subgroups or we want individual level causal effects, it's straightforward to pull those out as well. So to the first point, this is a figure from a paper by Vince Story and others, where they're reporting on the results of a causal inference competition that was run in conjunction with the Atlantic Causal Inference Conference. I believe this was the 2016 conference. And they're just comparing so this is a situation where they created a whole bunch of different data sets where they knew the relationship between the treatment, the covariates, and the response. And then they asked people to submit, these are so-called black box methods, basically automated approaches to try and estimate the causal effect across all of these. It ends up being 7,700 combinations of a simulation setting, different types of relationships between all of the included variables, and then 100 draws essentially from each setting. And I include this because I think it's really telling that, so we're looking at the bias and the root mean squared error in estimation of the treatment effect that is known in this case. And if we look at this, this is not something that is special to BART alone. All of these methods, so the oracle was when they actually put in exactly the model they used to generate the data, right? So, hey, that works. That's not surprising. But all of these from the second best after the oracle, and all of these very comparable methods, all the way over to superlearner here, hats off to Susan, and different combinations of superlearner and other ensemble methods, different variations of BART. But there's a few different things in here. But right before this sort of jump that we see to methods that still perform pretty well, but distinctly higher bias than over here, these are all methods that have a non-parametric fit for the response surface. And then over here, this was one that they came up with for the paper, but and it actually still falls pretty close there. They're ordered by root mean squared error. All of the rest of these empty circles are methods that don't. I think this tree strat had non-parametric fit to the treatment model. So, you know, there's not a proof here, but I think a very suggestive evidence that this flexible fitting of the response surface is really driving to a great extent the ability to avoid bias in causal inference here. And in this case, we know there's no unmeasured confounders because they generated the data. Nothing was excluded. And so in that situation, the flexible response surface seems to be a driving factor in the performance of automated methods, at least. So that's advantage number one. And then in terms of obtaining posterior distributions, it's a fairly straightforward process. So you first set up a test set of covariates, which is then going to be the procedure will provide draws from the posterior distribution for the response for all of the observations in your test set. You want to fit BART on the observed covariates in the response, and then you compute causal effects of interest from draws from the test set and the observed variables. So for instance, if we want to estimate a sample average treatment effect, we would create a test set that has all of the observations that exist in our data with treatment set to the opposite of what they actually received. Fit our model, and then for computing our causal effect, we're going to take the difference of the estimate for the response for whatever treatment was actually observed, and then this counterfactual treatment from our test set, changing the sign so that the difference is always treated minus untreated. And then we can average that across observations for each draw from the posterior. And so if we take 1,000 draws, we might have then 1,000 SATE estimates. And so that then becomes our posterior distribution for this causal effect. We can compute a mean credible interval from all of those draws. You could, in theory, get a true average treatment effect if you could construct a set of test observations that match the population distribution of the covariates. That's probably going to be highly difficult. You can also get conditional effects from BART as well. Or rather than doing all of this yourself, there now exists the BART cause package in R, which automatically sets this up. You just have to tell it, this is my treatment, this is my response, and this is the rest of the covariates, and it'll execute these steps for you. So for heterogeneous treatment effects, once we have a set of draws for each observation, true or counterfactual, and a number of draws from each distribution, we can compile them in other ways to estimate heterogeneous treatment effects. So this is from a paper that I was on looking specifically at a workshop on estimating heterogeneous treatment effects. And so here we can say, so this was a simulated experiment sort of based on real data where there is a fixed versus flexible, no, what's the other word? Anyway, mindset intervention, hoping to improve student achievement with some covariates measured. So here for each student, how successful do they expect to be in the future, ends up rated on a 7-point scale where 7 is the highest expected success, 1 is the lowest. And so we can say, let's compute our treatment effects within those levels of this ordered categorical variable to see if the impact of this intervention worked better depending on how successful students expected to be in general. And we can see that there's obviously a fair amount of uncertainty. We're taking smaller groups from subsets of the data, as you would with any subset analysis, but we can see that there's certainly a trend where the more expectation they have for success, the less the impact of this intervention is. So we were hoping to can't remember. And then we can also do things like, well, we'll make it a pairwise comparison and see are the highest ones with the highest expectations different from the ones with the lowest. So this is comparing groups 6 and 7 on the scale to 1 through 5. And so we have a posterior for the difference in the average treatment effect between those two subsets. And so we can do a sort of formal test for whether we believe that there truly is heterogeneity along the scale, at least in this particular format. So here, about 90% of the time in the posterior, the difference is positive, suggesting that there are larger, in this case, less negative ATEs for those two groups relative to the others. And all of this can just be done by manipulating the output of the model. So I don't have to go back and refit a model with the appropriate interactions to estimate the moderating effect of this new thing. I can just base it on the posterior distribution of the outcome for our test and training sets. All right, so there's a lot of tools out there, just FYI. I know of several R packages, at least. I am sure there are implementations in other languages that I am just not familiar with because I haven't learned them. So sort of the first was Bayes tree, which was put out by Chipman, George, and McCullough, who first introduced the Bayesian, the BART model. And then there is BART, which expands on that to include random effects into the BART fit, and also wrappers that do automatic cross-validation if there's things you want to cross-validate. Jennifer Hill and Vin Story have developed BART Cause, which depends on DBARTs, but implements functions specifically for causal inference. So you can tell it that I want to know the effect of this particular treatment, and it will take all of the steps that I've been talking about and give you, say, posterior distributions of that treatment effect. And then there's also TreatSense, which is usually available, although I have to fix a thing for CRAN right now. That includes sensitivity analysis methods for BART models. So I've been talking about the benefits of the flexible response surface modeling for controlling for observed confounding that still does not get away from the assumption that there are no unobserved confounders. And so we have developed a tool to assess how sensitive the BART-based estimate of our treatment effect might be to the presence of confounders that are unmeasured. And so that produces plots that look like this, where we are across a range of coefficients on our unobserved confounder, which is then tacked on in an additive way to the BART model. We don't really have a way of specifying how it fits into trees, but that there's some additive effect of the confounder. Similarly, an additive effect in the treatment model. How much does the treatment effect estimate change? Benchmarked by the coefficients that would be estimated for the actual covariates in the data set. So that's something that's available, which is nice from a causal perspective, just in terms of robustness, being able to say that, yes, this appears to be robust to violations of these assumptions that we can't assess in our data. All right, so basic points here. Nice things about using BART, we get the advantages of machine learning combined with the advantages of formal statistical inference, which when we're talking about causal modeling, I think is terribly important. You're not going to get a good feel for the confidence you have in your estimated effect without having some form of uncertainty attached to it. Computationally, it's relatively efficient. It is still a non-parametric model fit by MCMC, but does not require nearly as much time for cross-validation and such that other comparable approaches might take. It's been implemented robustly in R, at least, with several packages that help make it straightforward to get the answers that you seek when you're looking at a causal inference. Has demonstrated success in causal inference challenges. So I've submitted BART to 3, I think, and it's done very well every time. And has this sort of side benefit that once I fix whatever the problem is, there will again be tools available to assess the sensitivity to unmeasured confounding that is not captured by this flexible response surface modeling, to just give that added layer of hopefully robustness to causal inferences, or acknowledgement of vulnerabilities due to these assumptions that we have to make when making causal assessments, and cannot directly assess. And then also here's all of the papers that I have borrowed figures for. These Chipman et al. Papers are essentially the initial introduction of Bayesian of BART, citations for our packages, some other papers as well. And I guess with that, I would take questions.
Nicole, thank you so much for that introduction to BART. We have some questions already in the chat window, and I want to encourage other people to type questions in there if they like. But meanwhile, I will give you the first one, which asks, can you roughly describe the steps for fitting BART when one wants to estimate causal effects using propensity score stratification?
So, propensity score stratification. I mean, there has been some evidence that including the propensity score as a covariate in the BART fit, so it's just one of the X's essentially, does improve the performance, particularly I think with respect to coverage of confidence intervals. So it tends to be a little anti-conservative. And so in that case, what we have done is estimate a propensity score using, say, a BART model with now the treatment as our response rather than the outcome, and using that to estimate propensity scores, and then including those estimated scores then in the fit for the response surface. If you were to actually stratify, good question. Trying to recombine across strata might be a little hairy. So that my approach would be to sort of allow BART to figure out what strata are necessary by including it in the process of fitting the trees.
Thank you.
Sure.
A question that I have, you just mentioned the anti-conservative inference and the credible intervals. Can you talk about that a little more? I think I remember in the 2016 Atlantic Causal Inference competition, BART was the least biased, but there were coverage issues that then were kind of fixed and improved upon, and in last year's competition were just much better. So can you talk about that whole thing about confidence interval coverage and credible intervals and whatever else you can tell us?
Yeah, so yes, in the 2016 competition, which I showed you the results for bias and RMSE here, and you can see that BART, just plain old, where is it?
It's under the R. R equals 100, it's under the R.
But anyway, very small RMSE, and part of that is because it is underestimating the uncertainty in the results. So we do get coherent uncertainty estimate intervals, but what we found after this competition was that they were, I think, you know, if we were aiming for 95% coverage of the credible intervals, we were getting something in the low 80s, if I remember right. And this is a problem that, to my knowledge, no one has really figured out yet why this is happening, or what might need tweaking. So one approach was to take a multi-chain fitting. So rather than just do the MCMC, fit the BART model, essentially starting from different random seeds, do it several times and then combine those results, which helped. That improved it. Still conservative, but I think got it up to like, 90 or 87% coverage at nominally 95. And then last year, so to be perfectly honest, but the last competition, what we did was just inflate the estimated variances by 10% because we knew that it underestimated variability. Totally ad hoc. So I can't necessarily argue for that as a rigorously supported approach to dealing with anti-conservative tendencies in BART. We're still trying to come up with something that's a little more, rigorous. But that seemed to take care of the problem.
Thank you. I ran last year's competition, so yes, that did take care of the problem. But I'll also point out that when you combine BART with TMLE, which is on the slide that you're showing,
Yes, that helped too.
TMLE turned the asymptotically linear estimator, and then the coverage went right up close to nominal. I don't remember what it was.
That is absolutely true. Yes. So we're adding some. Yeah, go ahead.
No. I didn't want to interrupt you.
No, I was just saying, yes, adding that targeting step did seem to also correct for the issue. I was just rephrasing what you said. So go ahead.
Okay, so I want to encourage people to type in questions if they have them. Another one was just a small one about on slide 4. You mentioned Carnegie and Moo 2020, but that one's not in the reference list.
Oh, righto. Yes, that is going to be in Socius. It's a paper discussing using BART for predictive modeling in the Fragile Families Challenge.
I want to thank you so much for the presentation. It was very informative, and I cleared up a few questions in my mind, so I really appreciate your time today. Thank you very much.